friends here. I've got to find you, though. There you are. Okay. And Amari, you right? Jacori, got it. All right. Anyone else coming in since I called you on? Okay. Announcements that I can recall. The volleyball team, I believe, has a match tomorrow evening. I believe it's a home match, 6 o'clock, Birmingham West Campus, Arthur Shores Fine Arts Building, which is also our gymnasium. I can't remember now who they're playing. I think they played Bevel last night, and tomorrow night we'll play a different team, but I can't remember which one it is. Can't recall if there are any others. Any questions, any announcements you know about that need to be aired? Okay. Well, then we're in Chapter 2, Polynomials and Rational Functions. 2.2 are polynomial functions of higher degree. We did quadratics in 2.1. Now we're doing higher degrees here. And we are recording, so let's get the current slide up here. We're starting today with the intermediate value theorem. Now, what has many uses, but what today's use is this one. Let's suppose this implies that if you have 2 points, x equal a, of course y would then be f of a. X equal b, y would then be f of b. Here's x equal a, there's f of a. X equal b, there would be f of b. Okay? If those are 2 points on the graph of a polynomial function, as long as f of a is not equal to f of b, and obviously it's not here. If they were equal, you can't use intermediate value theorem. But if they are not equal, then for any number d that's in between f of a and f of b, any number in between, there has to be a number c such that d is equal to alpha c. Now, Zaria? Okay. I can't get my pen. Okay, anyone else come in since I called roll? Okay. Now, why this is true, and remember that we're talking about polynomial functions here. This doesn't deal for any function, polynomial functions. What are 2 features of polynomial functions? One of them is the only one we're interested in, but let's remember both of them. Like jazz. Smooth and continuous. Exactly. Here, all we're interested in is the continuity. Because if you have a value here, f of b, and another value here, f of a, and you have some value in between, because the function is continuous, there's got to be some c that's in between a and b that gives you that value. Can't happen otherwise. You can't get from here to there without going through that. So there has to be a c down there that f of c will equal to that value d. All right? That's how we talk about it. Here's how they express it. Let a and b be real numbers. These are on the x-axis, such that a is less than b. If f is a polynomial function, smooth and continuous, such that f of a is not equal to f of b. Now, if they're the same, there's no points in between them, so can't have that. So if f of a is not equal to f of b, then on the interval from a to b, inclusive, f takes on every value between f of a and f of b. May take on a few that are not in between there, okay? And here's Ty and Sharona. Okay, let's flick back the slide here. What if, let me get my pen set up. What if your function did this? That still could be a polynomial function, and there could be other values outside of f of a and f of b, but still every value in between f of a and f of b have to be covered. So it's not exclusive, it's not if and only if, it's just saying that f takes on every value between f of a and f of b, though there could be other values it takes on outside of that. What's more, it could take on every value between f of a and f of b multiple times. Now, I didn't draw mine to show that, but let's go back there again, and let's delete that one, and let's go like, okay, so there are values in between f of a and f of b that are not, that's fine, but it takes on every value in between, some of them a time or two, okay, or 3 or 4. Those are still could be polynomial functions as long as they're smooth and continuous, okay? Don't worry about that part. All we're interested in now is the parts in between f of a and f of b. Then f has to take on every value between that at least once, maybe more times. Why are we doing this? The intermediate value theorem helps to locate the real zeros of polynomial functions in the following way. If you can find a value x equal a, at which the polynomial happens to be positive, and you can find another value x equal b where the polynomial is negative, you know you have to have at least one zero in between those 2 points, because f of c has got to be 0 somewhere in there. Let me get Katie here. Y'all had a match with Bevel last night, right? Yes, sir. When? Yes. Good. And tomorrow night is who? Gadsden. Okay, good deal. And Tammy, right? All right, good deal. Okay. So, here's how we use the intermediate value to find those zeros. If you can find the x equal a where your f is positive, and another x equal b where it happens to be negative, because a polynomial function is smooth and continuous, takes on every value in between. There's at least one zero in between those two values. Gotta be. There could be several, but there's at least one. Okay? Then you can conclude that the function has at least one real zero in between those two values. Or, if x is negative, and if at x equal a is negative, at x equal b, the f is positive, then you know you got a real zero in between that. So it doesn't have to be positive negative, it could be negative positive. If the two values change signs, there's got to be a zero in between. So here's an example. Here's a function, f of x equal x cubed plus x squared plus 1. Okay? Now, they give you way too much information. They should have let you figure this out. But here's what I would have done. Okay? When x equals 0, this is obviously positive, right? Now, if you put in positive numbers here, that's going to be positive, that's going to be positive, that's going to be positive. It stays positive, right? So x equals 0, you know it's positive 1. So let's go on the negative side. Let's do a negative 1. Well, if you put in a negative 1 here, what do you get? Negative 1 plus 1 plus 1, that's still positive. So x is positive when f is positive when x is equal to negative 1. So let's leave 0 and go down to negative 1. Let's go more negative, like negative 2. What would this be? Negative 8 plus 4 plus 1 would be negative 3. Ho! At negative 2, at negative 1, this is positive. At negative 2, it's negative. Okay? So you know there's got to be a 0 in between negative 2 and negative 1. Well, you know it's not going to be an integer, don't you? Because there aren't any integers between negative 2 and negative 1. So here at this point, we start guessing. Okay? It follows from the intermediate value theorem that f must have a real 0 somewhere between negative 2 and negative 1. Okay? Now, it says it's shown below, but it's over there. Okay? Now, in the book, it's kind of below. I guess, yeah. Now, what you do from there is example, well, it's not quite example 6. I thought it was, but it's not quite. Okay? But anyway, this just tells you there is a 0 there. Intermediate value theorem guarantees it. Because it is a polynomial function, smooth and continuous, mostly continuous. So therefore, there has to be a 0 in between. By continuing that line of reasoning, you can find any real zeros of the polynomial function to any desired accuracy. That's an easy statement to say. It's probably going to be a little harder to do. But example 6 will show you how. Here's example 6. Almost the same function, but not quite. Use the intermediate value theorem to approximate, I'm not going to tell you exactly, but approximate the real 0 of this. And they only say one real 0. How many real zeros could you potentially have? 3, okay? But it's not guaranteed to be 3. It could only be 1, okay? They indicate it probably is only 1, okay? So let's figure out what they might be then. Let's pick an x. Pick an easy x. Easier. Yeah, right, I like it. Let x equal 0. So what is f of 0? 1, okay, because the first two are 0, okay? Now, let's just think for a moment here. When you start getting larger x's, you know that's going to be positive, that's going to be positive, but that one's going to be negative. But for 1, we still have this equals 1, because that would be 1 minus 1, which is 0, plus 1 is 1. Okay? And then you get larger still, this one takes over. 8 minus 4 plus 1, they just keep getting larger. So let's go to the left. Okay? Especially with this minus sign here, let's put a negative in here. Ooh, you know these got to be negative. So let's do 1 to the left. What you want to choose? Let x equal negative 1. So f of negative 1 is equal to, okay, I'm going to take this down further, okay? Okay, f of minus 1 is equal to what do you say? Negative 1. So, we know that we have a 0 in between x equals 0 and x equals minus 1. Right? Intermediate value theorem says you have to. What do you want to choose as another guess? What 0 could be? What value for x is between 0 and negative 1? Negative 0.1, 0.5. How about that? 1/2? Okay. Now, I don't know. Do you prefer fractions? Do you prefer decimals? Decimals, okay. Pull out your calculators. What is f of negative 0.5? F of negative 0.5. Negative 0.5 cubed is going to be a negative 0.125, I believe. And then minus 0.25, that would be a minus, I think it's going to turn out positive, but how much? Anyone do it yet? Second? 0.625. Okay? Now, we doubt if there's a 0 between 0 and 0.25, negative 0.5. Not very likely. There could be, but we know there's got to be a 0 between negative 0.5 and negative 1. So what next x could you choose? Negative 3/4? Is that what you said? I like it. Want to use fractions this time, or are you going to still go with decimals? Say again, decimals? Is that what I heard? Okay, negative 0.75. Punch it in, see what happens. See, we in the South are pretty violent. We punch our numbers in. Up north, when I was in Nebraska, they press buttons. They don't punch buttons. Okay, they're much calmer than we are. Okay. Anyone got it? All right. Nice. Yeah. Deal. Okay. Anyone got it yet? Second. 0.01. A little louder. That's fine. Okay. It's slightly positive. Okay. Well, guess what? Probably not likely it's between negative 0.5 and negative 0.75. So more than likely, it's got to be one between negative 0.75 and negative 0.1. Looks like we're getting really close to it with the negative 3/4. So what you want to try next? That's. Say again? Okay, you want negative 7/8. Okay, I should have gone down more with that one, but that is f of, if you want it as a decimal, that's negative 0.825. Is that right? 875, sorry. I knew that. So someone punch that one in. Anyone got it yet? What you got? Oh, we finally got a negative. Negative 0.43. Okay. All right. So negative 0.75 is positive. Negative 0.875 is negative. So it's got to be something between the two. And since this is so close to 0, I would guess something closer here than there. So maybe 0.8, negative 0.8. That's easy, going to be easy to punch in the calculator. So let's go with, I wish I'd left more room. Let x equal negative 0.8. Then f of negative 0.8 is negative 0.15. Okay, so it's still something between 0.75 and 0.8, and it looks like it's closer to 0.75. So what you want to try? Negative 0.76 maybe? Be okay? Let x equal negative 0.76. F of negative 0.76 is what you get? All right. Well, here we have a positive 0.01 at negative 0.75, a negative 0.01 at negative 0.76. I would say we're awfully close. I believe I would just settle for a negative 0.755 and say we're going to be close enough. We're already within 2 digits of precision. You got to be. So therefore, I'd say negative 0.755 is going to be close enough. Let's see what, oh my goodness, look what the book did. Okay, I'm going to clear this. And how they start is begin by computing a few function values. We did, but we didn't get this silly about it. We didn't go to negative 2 way down there, negative 1. We did that one. 0, we did this one. We just tested 1 and saw that was out of the question. So we narrowed down between those two. Because f of negative 1 is negative and f of 0 is positive, you can apply the intermediate value, conclude has a real 0 between negative 1 and 0. So they chose to pinpoint the 0 more closely, divide the interval into tenths, okay, and evaluate the function at each point. They just magically go to negative 0.8 and negative 0.7 because they knew the answer, and they found out this one's negative. It's positive. I think we got those same answers. We may not have done negative 0.7. So then you go to something in between those. So you have to have a real 0 between negative 0.8 and negative 0.7. Okay? And they show the figure. I don't know why they didn't do that earlier. They say for a more accurate approximation, compute the function values between those two. And when you get one that's like this one's down here, this one's up here. If you choose something here and you get here and here, then something between these two. And you just always bracket between the positive and the negative functional value. Okay? Keep applying the intermediate value theorem just like we did. And ultimately, by continuing the process, you can approximate the 0 to any desired accuracy. Now, there was an ancient mathematician and scientist and engineer named Archimedes. Lived like 400 BC or something. I mean, way back there. He was a brilliant character. They didn't have formulas. They didn't have calculus. They didn't have really very much to do. He was able to figure out way more stuff than just about anyone else had even dreamed of. And he was estimating the area of a circle. And he was doing it by a procedure a lot more complicated than this, but still, it was lots and lots of calculation, get closer and closer and closer. And he called his method the method of exhaustion. When he got tired of doing it, he said, that's close enough. Okay? And that's basically what we're doing too. Any desired accuracy, when you get tired, say, okay, that's close enough. Okay. Whoa, they don't even show it. But in your book, it shows x equal negative 0.755 is an approximation to the nearest thousandths of the real 0. Okay? And by the way, there is a checkpoint. Please pay attention and do the checkpoint soon after class as you can. All right, vocabulary, top of page 132. Any questions on 2.2? Okay. The graph of a polynomial function is blank, which means that the graph has no breaks, no holes, no gaps. Continuous. Very good. Number 2, the blank, blank, blank is used to determine the left hand and the right hand behavior of the graph of the polynomial function. What do we do when we want to know what's happening in the long run this way or long run that way? Say again? I can't hear. Okay, they call it leading coefficient test. I prefer leading term test because the whole term tells you information, not just the coefficient. Okay, but that's fine. That's what the book calls it. Number 3, a polynomial of degree n has at most how many real zeros? N, and at most how many real turning points? N minus 1. Very good. When x is equal to a is a zero of a polynomial function, the 3 statements below are true, but you got to fill in the blank. One of these is x equal a is a blank of the polynomial equation f of x equals 0. What did we used to do with equations? Jeremiah, right? What do you do with equations? Second?
It's a solution.
Yes, it's a solution. We solved it, okay? Number B, blank is a factor of the polynomial f of x. Factors usually show up in parentheses. What would you have in that parentheses? If x equal a is a solution or a zero, say again, x minus a would be the factor. Perfect. And number C, the ordered pair A0 is an blank of the graph of f. X-intercept, you got it. Number 5, when a real zero, x equal a of a polynomial function f is of even multiplicity, the graph of f blanks the x-axis. When it's even multiplicity. Second?
It just grazes it, it touches it.
I can't hear.
It touches it.
Touches it, perfect. I usually say kisses it, but that's probably a little too intimate. Okay. And when it is of odd multiplicity, the graph of f blanks the x-axis, x equal a. Crosses it. Now, if it's a large odd multiplicity, it will hang around that for a while, but it still crosses. Okay. Number 6, a factor x minus a raised to the kth power, when k is greater than 1, yields a blank blank x equal a of blank k. Basically, the answer is almost in number 5. One of the answers is. The blank k, that word's in number 5. Say again? A little louder? Someone may be saying it. Say again? I can't hear. A little louder. Oh, okay, sorry. Number 6. A factor x minus a raised to the kth power, where k is greater than 1, yields a blank blank x equal a. That answer, one of those words is actually
Repeated zero.
Is what?
Repeated zero.
Repeated 0, x equal a of blank k. Multiplicity k. Perfect. Okay. Number 7. A polynomial function is written in blank form when its terms are written in descending order of exponents from left to right.
Standard.
Second? Standard form. That's okay. Yeah, polynomial function. Remember, we didn't say it's standard form for the quadratic. Quadratic, we have a different standard form, but for a polynomial function greater than degree 2, that would be the case. Number 8, the blank blank theorem states that if f is a polynomial function such that f of a is not equal to f of b, then on the interval between a and b, f takes on every value between f of a and f of b. Intermediate value theorem. We just did it. And again, I've assigned some of these before, and let me say it again. I would do all of the problems 9 through 14. It's just matching with these graphs you see on the left-hand side of the page, bottom half of the page there. You should be able to do them all. The back of the book and Calc Chat will only give the odd number answers, but you should be able to figure out the even as well. Then do either 15 or 17. They're both at Calc Chat. 17's at Calc View. Do any of the odds 19 to 27. They're all at Calc Chat. 21's at Calc View. Do either 29 or 31. They're both at Calc Chat. 33 through 47. They're all at Calc Chat. 43's at Calc View. 49 or 51, both at Calc Chat. Any of the odds 53 to 61, all at Calc Chat. 59's at Calc View. Any of the odds 63 to 69, they're all at Calc Chat. 67's at Calc View. Any of the odds 71 through 83, they're all at Calc Chat. 73's at Calc View. 85 or 87, they're both at Calc Chat. 89 or 91, they're both at Calc Chat. 89's at Calc View. And then do any of the odds that you would choose, 93 through 97. They're all at Calc Chat, should be. Then there's true false, either 99 or 101. They should be at Calc Chat. And then 103 or 103 or 105. They should both be at Calc Chat. And then you can think about doing 107 if you choose. It should be at Calc Chat as well. Any questions? 2.2. All right, good deal. That ends 2.2. Let's move on to 2.3. And where in the world did my... Sometimes it forgets it has a flash drive in it. It has forgotten. There. I have a suspicion what goes on there, but I don't know for sure. All right, moving on to 2.3. Now, after 2.3, quiz time, okay? And I'll probably have that ready for you on Thursday, okay? I sort of wish I had it today, but we will, I'll get it to you Thursday. Whether we finish 2.3 or not, that way it gives you an extra weekend to work on it. Which reminds me, folks, now, I don't have all the grades in Blackboard yet. I'm going to try to get those done this morning. But there's several people who I can't tell if you're coming back to finish your test or not. Because you have do not grade or not finish or something on there. I have everything graded you've done so far, but I don't know. So if you don't see, after sometime this morning, don't see your grade on Blackboard, that means I'm not certain. So come and let me know. No, I want this grade, or no, I'm going to work on it some more. Please get those wrapped up, because we're ready for quiz on Chapter 2 almost. All right, Chapter 2 is still, Section 2.3, quiz on Chapter 2. Polynomial and rational functions, okay? Just as before. We're still on the polynomial part. This time we're doing polynomial. What they mean is polynomial division and synthetic division, okay? So we're going to do both of those. We're going to use long division, that's what we usually call it, not polynomial division, to divide polynomials by other polynomials. We'll use synthetic division to divide polynomials by certain binomials of the form x minus k. And then we'll use the remainder theorem and the factor theorem to give us all sorts of good information. Okay? So let's first do the long division of polynomials. Before we do this, let's go back, and I'm going to review long division. I know y'all are really good at it, but let's review it. Let's say we have 12 into 619164. 619164. I didn't quite make up the number, but it's there. Okay? How do we do long division? And don't pull out your calculator and say, here's how you do it. We need actually to be able to do the long division. Anyone remember how to do this? This is so long ago. Oh, good deal. How do we start? Okay. One thing about division that's different from multiplication, addition, and subtraction. Adding, subtracting, multiplying, we usually start from the right and move to the left. With division, we start from the left and move to the right. So what you're saying you were going to do? 12 into 61. How many times will that go? 5 times. Then what do you do? Multiply. What does that give you? 60. Then you do what? Subtract. What does that give you? 1. Then you do what? Bring down the 9. Then you do what? Divide again. 12 into 19. 1 time. What do you do now? Multiply. What does that give you? 12. What do you do next? Subtract, and that gives you 7. Then you do bring down the 1. Then you do what? Divide. 12 will go into 71. How many times? 6 times? Don't think quite. 5 times. Okay, let's do the 6. Since it was said, we're going to do that. Okay? There's a reason for this. Okay? It almost does it, but it doesn't quite. But we'll see what happens. When you do a 6, what do you get? 72. Guess what? You can't subtract that, can you? So therefore, you got a little too much, so we go back and change to a 5. But actually, I'm going to be dumb about it, and I'm going to change it to a 4. Okay? I know it's not going to work, but what happens if we did a 4? Multiply that, and what do you get? 48, and then you do what? Subtract, and what do you get? 23. And what do you say now? Whoops! Okay, or whoopsie? Okay, or something like that, because your remainder cannot be greater than your divisor. Okay? That's why I did it. If you get a remainder, you see, notice this remainder was 1. That's less than 12. This remainder was 7. It's less than 12. This remainder, 23, greater than 12, you can't do it. You have to go up a number. So that was a dumb choice, but it was purposely done. Okay, so what did we decide on? It wasn't 6, it wasn't 4, it was 5. And what does that give you? 60. And then you do what? Subtract, and that gives you 11. 11 is less than 12, just barely, but it is less than 12. And then you do what? Bring down the 6. Then you do what? Divide again. What does that give you? 9. Then you do what? Multiply. That gives you 108. Then you subtract. That gives you 8. Then you bring down the 4. And it goes to 7. Wow. Okay. 84. Now, what does that mean? It means several things, but what does it mean? Number 1, notice you have a remainder of 0. If you have a remainder of 0, that tells you 12 and 51,597 are both factors of 619,164. They are exact factors. Okay? It divides into an exact number of times. If you had a remainder, that means they're not factors. Okay? So this one, they are factors. Y'all are really good at your long division. Congratulations. Okay? So let's go to, suppose you're given the graph of f of x is equal to, and what if you even weren't given the graph? Who cares? Okay? But where you're given the graph of 6x cubed minus 19x squared plus 16x minus 4, and on that graph it looks really close, exactly that it looks like it crosses exactly at x equal 2, meaning 2, 0, looks like it's an x-intercept, okay? That the a0 of alpha occurs at 2. Now over here, I can't tell what's going on. looks like two different points, or maybe I just drew the graph poorly and it's only 1 point, but I can't tell what each one of them are, but it looks like we have either 1 or 2 zeros in between 0 and 1, but I can't tell where they are or even if they're really two different zeros. But it sure looks like x equal 2 is a 0. Okay? Now, because x equal 2 is a 0, tell me 3 other things about x equal 2 that you can get out of that. Oh, we just did that in our vocabulary. Long time. Ooh, short memory span. Okay. That means that x, we just said one of them, 2, 0 is an x-intercept. X equal 2 is a solution to the function f of x equals 0. And what's the other one? Oh, and x minus 2 is a factor. Ha! Yeah, there it is. You know that x minus 2 is a factor of f of x. Okay? Because x is a 0, or at least you suspect it is. That means that there must exist a second degree polynomial, because this is third, that's first. There has to be a second degree polynomial, q of x, such that if you do f of x equal x minus 2, that's one factor, times the other. Just like we had 12 times that 51,000, blah, blah, blah. Those were just factors. If x minus 2 is a factor, then whatever the thing. The other polynomial is. How do you find that? Do long division. If these two multiply to give you this, divide f of x, which we know, by x minus 2, which we're guessing, and see if we can get a q of x. So that's why we need to do long division. So let's see if we can do it. That should be example 1. Here it is. Divide that. Okay? Now, the big number, the one that says divide, that's called the dividend. That goes inside the house. 6x cubed minus 19x squared plus 16x minus 4. And then outside the house, what you're dividing by is x minus 2. Warning, 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 okay? Be sure that both the divisor is in descending order of power and that the dividend is in descending order of power. What's more, make sure that every term is accounted for. Here, what's your exponent? 1. What's the exponent here? 0. What's the exponent here?
1, 0.
Yes, you're not missing any. So we're perfectly fine to go like this. Now remember, how do we do division? Left to right. So we start with the leftmost term here and divide it into the leftmost term here. How many times will x go into 6x cubed? Well, what's your coefficient here? 1. How many times will 1 go into 6? 6 times. And we'll say again?
X squared.
X squared. Perfect. Okay? So there we did the division part. What was our next step? Multiply. So multiply 6x squared times x. What do you get? 6x cubed. You better. That's what you just divided. So you better get exactly the same thing. Then you do the next term. 6x squared times minus 2 would be, say again? Negative 12x squared. Perfect. Then what do we do next? Subtract. Now, I have a little pet thing to do. When you get in with sign numbers, my thing is you go with the rule for sign numbers. Change signs and add. That helps me avoid errors. So if I change the sign and change this to a minus and that to a plus, now add them, this adds to 0. Okay, that's why we did it. Okay, what does that add to? Negative 7x squared. See, those signs, they're there to trip you up, so be careful with them. Then what you do next? Bring down the next term. plus 16x. Okay? And then we do what? Divide again. X will go into negative 7x squared. How many times? Negative 7x times, right? And then what do we do next? Multiply. Negative 7x times x will be negative 7x squared. And negative 7x times negative 2 will be, second, plus 14x. And then what do you do next? You subtract, but I like to change signs and add. So I'll make that the plus and make the next one a minus. Now it's easy for me to do because I have the magic pen here, but however you want to do it. So when you add these two, of course that first one disappears. That's exactly why we did it that way. What's your next one give you?
Negative 2x.
2x. Okay, and then what do you do? Bring down a minus 4. Don't forget the sign. Okay? And then you do what? Divide, and what does that give you? Say again? Plus 2. Okay? And then you do what? Multiply. 2 times x is 2x, and 2 times minus 2 is negative 4. Ding, ding, ding. We have a 0 remainder. That means, sure enough, this was a factor of this thing, and the remaining factor is 6x squared minus 7x plus 2. All right. Well, that just factored it one time. You've got two factors, x minus 2, which we thought was going to be 1, and this one we've confirmed it is an exact factor of this one. Can we continue factoring that? How? Okay. There are 3 means at your disposal. One is trial and error. And that works on real simple ones. This one's a little more complicated. Okay? Now, usually what I do then is go to the AC method. Have y'all ever heard of that? Okay. Some people call it by different names. Someone the other day called it, I know Ms. Stringfellow used to call it scissors method. I've heard several names for it. But anyway, what we do is multiply A times C, and what does that? AC is equal to 12, and B is equal to minus 7. Okay? So AC is 12, and B is minus 7. Okay. Now, what we're going to do here is come up with factors of 12 and see if we can get any of them to add to a minus 7. Now, what does that tell you? If the product has to be 12, but the sum has to be a minus 7, they both have to be negative, okay? Because the only way you get a positive product is for both to be positive or negative. If the sum is negative, they both got to be negative. So, maybe you can come up with one right off the top, or you might need to do a little work. Both negative, so how about negative negative 12. That adds, multiplies to be 12, but it adds to be minus 13. So that doesn't work. What's the next one? Minus 2 times minus 6. That multiplies to be 12. It adds to be negative 8. Ooh, so close, but no cigars. So that doesn't work. Negative 3, negative 4. That multiplies to be 12. It adds to be negative 7. Ding, 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 we have a winner. Okay. Now, so what we do with that, because our B was this middle term, we split that into these two terms. So we put the 6x squared, just like it is, and then rather than minus 7x, we do a minus 3x minus 4x, because that's what we were adding to make minus 7, right? and then we leave our plus 2 as it is. Now it looks like we just made it worse. We started with a trinomial, we wound up with a quadnomial, okay? But what can we do with this that we can't do with that? Group them, okay? Don't group them, okay? Now, are there any common factors in the first group? 3x. What's left? 2x minus 1. Is that what I heard? Say yes? Okay, good. All right. In the second group, are there any common factors? A negative 2. And then what's left? 2x minus 1. Ding, ding, ding. We have another winner. Okay? Any common factors there? 2x plus minus 1. 2x minus 1. And what do you have left? 3x minus 2. Okay. Now, remember what the thing of being a factor is? That if you had set this equal to 0, which we should have done and I forgot to do it, then this is going to be equal to 0. Where do you go from here? Second? Set each of them equal to 0. So 2x minus 1 equals 0, or 3x minus 2 is equal to 0. That first one does what for you? What do you do? Not subtract. Add 1 to both sides, and that gives you? That gives you 2x is equal to 1. X equal 1/2. You divide both sides by 2. I'm running out of room, so I skipped that step. What do you do on the second one? Add 2 to both sides. And what does that give us? 3x is equal to 2. And what does that give you? X is equal to 2/3. Now let's think back to our graph. X equal 1/2, X equal 2/3. Let's look at that. That one could be X equal 1/2, and that one could be X equal 2/3. I can't tell looking at it, but it sure seems reasonable. So it looks like we do have 2 more zeros right there. We've just found them. It says use the result to factor completely. Oh, I'm sorry. All they said was factor completely. Sorry, I took you too far. No extra charge. Factoring completely, this thing will be x minus 2. They actually gave us that one. Now, 2x minus 1 times 3x minus 2. That's all they said to do. We went further and got the zeros. We knew x equal 2 was 1. We got 2 more. Okay? Anyone need this a little longer? Okay. See what we've done. Sort of messy all over the board. By erasing it. All right. Everybody got it? Okay. So let's erase this and see how they do it. Okay. Oh, I didn't need to erase it. They went to a new slide. Exactly like what we did, except they like to indent and do the x squared over x squared. I don't care. To me, I'm doing this into this. I just assume write it up here. But you can write it anywhere you want to. The important thing is to keep up with things. Okay? And they did exactly like we did. First term in the first term, x in the 6x cubed, 6x squared. You divide first, then you multiply. 6x squared times x is 6x cubed. 6x squared times a minus 2 is minus 12x squared. Now they subtract, that's what they say. I suggest you change signs and add, which is subtracting sign numbers. Change sign, add. Those go to 0, which they've got to. That's why we chose them that way. This gives you a minus 7x squared. Because it's so easy to make mistakes subtracting sign numbers. Okay? Then you divide again, x into minus 7x squared will be a minus 7x. Then you multiply again, negative 7x times x will be negative 7x squared, and negative 7x times negative 2 is plus 14x. Now you subtract, which I call changing signs and add. Make that the plus and this the minus. That goes to 0. This gives you a plus 2x. Divide again. I keep forgetting. We'll bring down the other. Okay, x into 2x will be plus 2 times. 2 times x is 2x. And 2 times minus 4 is minus 4. The remainder 0 tell you these are factors of that. They multiply exactly. Okay? Because that remainder was 0. Now, because they said factor completely, we then see if we can factor that. And by the way, what are our other methods? I said you could do trial and error, which I thought might take a while. AC method was the second. What's the third way we could have found out the zeros for this? Quadratic formula. Remember? d squared minus b plus or minus square root of b squared minus 4ac over 2a. That would have given it to you. Okay? It's a little bit longer, but it's easy to do. Your numbers are there. Okay. From that division, you can conclude that this thing factors into x minus 2 times that quotient. Okay? And by factoring this quotient, and they don't tell you how they did it, they just said they did, you get these two pieces. Okay. That's all they said to do was factor them completely. And that's what we did. Let's see if they do any more to it. Okay? I don't guess so. In example 1, x minus 2 is a factor of the polynomial that. The long division process produces a remainder of 0. Often the long division will produce a non-zero remainder, meaning that was not a factor in the first place. Okay, if you get a non-zero remainder, that means it wasn't a factor. Okay, and here they do another long division. If you divide x squared plus 3x plus 5 by x plus 1, and you do your division, x will go into x squared, x times x is x squared, x times 1 is x. Change signs and add. This one's easy to subtract. 0 here, 2x there. Divide again. Oh, bring down the 5, plus 5. 2, x into 2x is plus 2 times. 2 times x is 2x. 2 times 1 is 2. Here, when you subtract, you don't get a 0 remainder. You get a 3 remainder. Okay? Now, at this point, you know this is not a factor of that. This is not a factor of that because there is a remainder. Here's the key about remainders, though. Remember, the remainder has to be, remember back before when we made our poor choice of dividing numbers, you got a remainder greater than the divisor, you knew you had to go another time. Well, now, the remainder has to be a lesser degree than this one. This is first degree, that's 0 degree. You have to go until your remainder is less degree. Here your remainder was the same degree, here your remainder is less. That tells you, sure enough, you're through. That's as far as you can go, and there's your remainder. Okay. I don't know where they were heading with that. And how did my computer get unplugged? My battery doesn't hold well, so I'll try to keep it plugged in. But it did better than it usually does. All right, in fractional form, how we express what we had here, I don't know if you remember this, but you take your remainder, you would say your answer was x plus 2 plus 3 over x plus 1. Remember when you did that? When you did, if you had a remainder when you divided numbers, then you took your remainder, put it over the dividend, and that was your fractional form. Same thing here. And that's what they're doing on this page. You can do this way. X squared plus 3x plus 5 divided by this is equal to your quotient plus the remainder over your divisor. Same thing as we did before. That's one way to write it. Okay? Here's the other way. Multiply everything on both sides by x plus 1. Now that leaves, you get rid of this denominator, get rid of that denominator. That looks good. So you have x squared plus 3x plus 5. But you multiply this by x plus 1, 2. X plus 1 times x plus 2 plus 3. Okay? So that form is dividend is equal to quotient times remainder plus quotient times dividend, divisor plus remainder. Sorry about that. Those are both forms of what they call the division algorithm. Why they call it that, I'm not sure. It sounds really good though, doesn't it? Okay? All right. So here's the division algorithm. If f of x, that's your dividend, the big polynomial, and d of x, that's your divisor, the little polynomial, are polynomials such that d of x is not equal to 0, because you can't divide by 0, and that the degree of d of x has to be less than or equal to the degree of f of x. Could be equal, but it has to be, d can't be greater degree than f. F has to be greater than or equal to the degree of d. Okay? Then there exist a unique polynomials, q of x, quotient of x, and r of x. Now, that r can have variables in it, r of x, such that the f of x, your dividend, is equal to the divisor times the quotient plus the remainder. All these now can be functions of x. For r of x, if this r of x is equal to 0, that means you have these are factors, okay? Or the degree of r of x has to be less than the degree of d of x. Has to be, otherwise you haven't finished dividing. Okay. If the remainder r of x is 0, then d of x divides evenly into f of x, and they form factors. D of x and q of x are factors. Only if that r of x is 0. And again, the other way you could write this is divide everything by d of x. Write it as f of x over d of x is equal to q of x plus r of x over d of x. That works too. There it is. Also be written this way. F of x divided by d of x equal to q of x plus r of x over d of x. What we first said. In the division algorithm, the rational expression f of x over d of x, this one, is improper. What makes it improper? The degree of the numerator is greater than or equal to the degree of the denominator. That's what makes it improper. The improper fraction, 17 over 3, because 17 is greater than 3. But if you wrote that as 5 and 2/3, then it would be a mixed number, and 2/3 would be a proper fraction. Okay? For polynomial or for rational expressions, improper means degree of the numerator is greater than or equal to the degree of the denominator, which it has to be to do your division. Okay. On the other hand, the rational expression r of x over d of x has to be proper. The degree of the remainder has to be less than the degree of the divisor. Okay, because the degree of r of x is always less than the degree of d of x. Okay. Now, what I said already, here they're saying now. Before you apply the division algorithm, follow these steps. Before you do long division of polynomial functions, do these two things. Make sure the dividend, the big one, f of x, and the divisor, the little one, are in descending powers of the variable. Okay? 3, 2, 1, 0, blast off, whatever. Okay? Now, also, if you're missing a power, insert a placeholder with 0 coefficient for the missing powers, because you've got to account for every power. And we're going to see an example of that coming up really soon. Okay. What? They're jumping to synthetic division. They're skipping examples 2 and 3. So let's us go back and do, there, we'll do it right here. Example 2. Divide x cubed minus 1 by x minus 1. Check your result. What goes where? One thing in the house, one out of the house. What goes where? X minus 1 goes out of the house. What goes in the house? X cubed. Aha! What'd you say?
Plus x squared.
Nope, you can't put in an x squared. That wasn't in here. A 0x squared. That's still 0, but you have to account for every term. See, this one you got 1, 0, you're fine. Here we don't, so we have to put in. So what's next? 0x. You have to account for every term. And what's next? Second? Minus 1. Perfect. Now you begin your division. X will go into x cubed. X squared times. Then you do what? Multiply. X squared times x is x cubed, and x squared times a minus 1 is minus x squared. You see why you have to have that term there? If you put the minus 1 there, you'd be all messed up, okay? You have to have, can only add or subtract like terms, okay? So change signs, add, make that minus, make that plus. This adds to 0. What does that add to? Second, x squared. And then you do what? Bring down nothing, okay? 0x, okay? And then you do what? Divide again. X will go into x squared. X times. Then you multiply. X times x is x squared. X times minus 1 is minus x. And then you change signs and add or subtract, whichever you want to say it. I'll make that a minus, that a plus, and add. That goes to 0. And what does that go to? X. Bring down the minus 1, and what does that? Plus 1 times, and that goes exactly x minus 1. 0 remainder. So that does factor, and it factors completely. But guess what? Y'all knew that, didn't you? You were just hiding on me. You knew that x cubed minus 1 will be divided by x minus 1. Why? Because you knew how to factor the difference of two perfect cubes, didn't you? Yeah, the first one is just the cube root of each one, x minus 1, with the same sign in between. And then remember the next step? Square the first, x squared, opposite the product of the two, not twice, opposite the product of the two, plus x, and then square the last plus 1. And that's exactly what we got here. So you knew that, didn't you? But this just confirmed it. If you didn't want to remember the formula, you can always do division. Okay? See how that works? All right. And there is a checkpoint following. Okay, now the question is, will we have time to do example 3? And the answer seems to be no. Okay. I don't know if that's a real answer or not, or a desired result, okay? But we'll assume not, and we'll start with example 3 next time. Let me give you a few homework exercises in this set. Do number 7. It's at calcchat.com, okay? Do number 9. It's at calcchat.com. Do any of the odds 11 through 21. They should all be, 11 through 23. They should all be at CalcChat. 19 should be at CalcView. Okay? Hold off there. Those are all long division problems. Now, a couple of those at the end, especially number 23, what you have to do is actually multiply x minus 1 cubed and then divide that into x fourth. That's a little more involved, but it is doable. Okay? Oh, wait, let me back off some. Let me change that and say just do 11, 13, 15, 17, 19. Stop at 19. We'll do the next after we do the next example. All right, good deal. So only go through 19, and they're all at Calc Chat 19. Good deal. I cheated you out of 1 minute of your tuition dollars. I am so sorry, but there is no refund. None whatsoever. Okay.